So it's 12 noon. We'll get started. Good afternoon, everyone, and Happy New Year to all of you. And thank you for joining us for a new year of Medical Grand Rounds. Before we begin, I'd like to make a brief land acknowledgement. McGill University is on land which has long served as a site of meeting and exchange amongst Indigenous people. We acknowledge and thank the diverse Indigenous peoples whose presence marks the territory on which people of the world now gather. Before we begin, I'd like to remind you to please leave your questions to the end of the presentation. Please enter them in the chat. As well, please remember to fill out a brief survey that will be sent to you following the presentation. This will let us know that you were present today. And finally, I'm very excited for today's lecture. One of my colleagues, Dr. J. Brophy, will be presenting, and I'd like to invite Dr. Nancy Mayo, one of our own professors, who is a distinguished James McGill professor and an amazing member to have on our team, to introduce Dr. Brophy today. Nancy, the floor is yours.
Thank you. Is this a good place to stand?
It's fine.
Jay says very short, very short. So it's my pleasure to introduce to you today Dr. James Brophy, although I'm sure he needs no introduction, as he's one of McGill's and Canada's leading clinical scientists and epidemiologists. And you can read his bio on the page. As you can see from his bio, he had an eclectic educational voyage to get to where he is, starting in engineering, medicine, and ending up doing a PhD in epidemiology and biostatistics, where he is a full professor in the department and in the Department of Medicine. And he has a very eclectic research background. So in reading his bio, it gives an idea about his interests and expertise, but this does not tell a complete story. To quote from one of his recent papers, numbers don't lie, but they only tell part of the story. This bio only tells part of his story. Jay is an incredibly gifted, productive, and ethical researcher. On PubMed, he's identified as participating in more than 250 publications. In the past 2 years, he has participated in 21 publications in very diverse areas, not just his own area in cardiovascular health, but in HIV, cancer, maternal child health, sarcoma. And that's because Jay is a great collaborator, sharing his research expertise with many research teams. And I can speak to that because he helped me out many years ago in some of my projects, so he gained some expertise in rehabilitation as well. I've always been very proud to have been able to count Jay as one of my colleagues and one of my friends. So please welcome him to this seminar series. I'm sure his talk will be novel, thought-provoking, and exciting. Thank you, Jay.
Thank you very much, Nancy. I no way I could live up to that. I should definitely tell my family to retain you for my obituary, which hopefully is not going to occur in the next hour. But anyway, thank you ever so much. So I have no conflicts of interest, and this is perhaps not the typical conflicts of interest slide, but it does represent a little bit who I am. So this is going to be a little bit different for Department of Medicine, I think, in that we're going to talk a little bit about probability, statistical inference, and then some of it, the practical implications and applications of these concepts. So I think a good place to start is, are stats and math in general important for MDs? A study from about 10 years ago, and you can see that physicians are in that upper right-hand quadrant where obviously we require social skills, although not all our colleagues always display them, but in general, I think we do have good social skills. But we also need math skills. And I think that hopefully this talk will reinforce the importance of having not only our good clinical social skills, but also to develop and maintain some math skills. As an overview, what might be some of the benefits of having a good stats knowledge? Well, for the producers, the clinical scientists, the clinical researchers, I think it helps you in the design, collection, analysis of your data, It enables you to recognize and acknowledge the uncertainty around your results. This is a big problem, I think, when people underestimate this, particularly when they're giving press releases, etc. In the published literature, they're a little bit more careful, but things get kind of slack when we do interviews for mass media. It also help you in the interpretation and the presentation of your results. For those of us who are just consumers of clinical research, I think a good stats knowledge also helps in appreciating and understanding new knowledge, in the formation of reasonable conclusions, and most importantly, in eventually making good decisions for our patients. So this is the meta-science of the hypothetical deductive model of the scientific method, where we start with, in the upper right-hand corner, we generate and have a specific hypothesis, design our study, get our data, analyze it, interpret the results, publish, and often from those results, we'll generate new hypotheses, and the wheel goes round and round. This talk today is going to be centered in the lower left, where we are looking at the analysis and the interpretation of our results, and where we sometimes have some issues. But of course, there are many other places where this cycle can go wrong, where we don't have the time today to go into it, but forming hypothesis after seeing the results, harking, p-hacking, bias, etc. But we're going to really be concentrating just on the stats part of it. So, statistical inference. I think first of all we need a little bit of a definition, and I think of it as learning from our sample about the underlying population that we are interested in. And if we can't do this, then we're just left with a bunch of data. So I think statistical inference is obviously very important. The trouble is, of course, that our samples are noisy. There's lots of uncertainty, lots of variation. And so to properly form these inferences, we have to refer to some common statistical distributions. Alternatively, we can do simulations, but we're really going to concentrate more on referring back to common statistical distributions. So, but just as a caveat, before we go down that road, just to remember that even though this is a lot of a stats talk, if you want, that statistical models alone are insufficient for determining causality, right? And we've been taught this, with lots of little pithy aphorisms like association is not equal to causation. So just to keep that in mind as we go down and get excited about the stats, or at least some of us get excited about the stats, that there is this sort of other element that we should not lose sight of. So what are the basic, or some basic probability distributions? And the point of these is that, if we're going to understand probability in general, we have to understand these distributions, because these are what we're thinking are the distributions that could have generated our data. And then we can kind of begin to analyze our data. And so commonly, probability distributions go down two different routes, depending on whether you have discrete data or you have continuous data. On the discrete side, we have the binomial and the Poisson distributions. On the continuous, we have the normal distribution and uniform. Now, there are, as we'll see, there are variants on this, but just to give you a rough idea of where we're going. So the normal distribution, we're all reasonably familiar with. That's the lower figure on the right. Why are we familiar with it? Well, because we see a lot of it in the natural sciences due to the central limit theorem. There are lots of variables that are normally distributed. There is a mathematical formula. You'll be tested at the end of the talk to see if you can retain this, but essentially the visual image, I think, is what we want to keep in our mind. Sometimes we have a T distribution, which is normal in shape, but has fatter tails, as we can see from here. This is how fat the tails are depends on something called the degrees of freedom, right? This is the one on the top there is just with 3 degrees of freedom. We also can measure the area under these curves, right? And then that becomes, instead of a probability density function, it's called, surprisingly, a cumulative probability density, okay? And so that we can measure the area underneath the curve, we can measure the area between 2 points underneath the curve, and this can give us, and does give us, measures of probability. This is taking those 2 curves and going from left to right, just accumulating the area under the curve, right? And so we can see for the normal, if we have what we call a Z point at 1.96 in the bottom curve, then above that is 2.5% of the area. And similarly, if we're below minus 1.96, we have another 2.5%. And so we can calculate between the two of them the area of 95%. And this is just showing that in a different manner, just showing the cumulative. So going from the same areas, if you have a normal distribution, and you have 95% of the area, if you take those same points and you were assuming that it was a T distribution, you would only have 86% of the area. So it depends what model you choose. So, when we get into this argument about Bayesians being subjective and frequentists being objective, bear in mind that the frequentist has to make all sorts of assumptions too about what model his data he thinks has generated his data. So the frequentist is really no more objective than the Bayesian. The uniform distribution is one that we really only use in Bayesian statistics when we want to say, look, we don't really know anything. We want our analysis to depend only on the observed data. And so we use our prior as this non-informative uniform distribution. So when we get into discrete data, we refer to binomial distributions, right? And there's an equation where we can actually count out and figure out, according to how many trials we have and what the probability of success is, we can actually figure out what's the probability of X number of successes in trials. This is important. This is particularly really only useful when you have a binary outcome, right? Dead, alive, hospitalized, not hospitalized. And this actually, of course, forms what's the backbone of something we see all the time in the medical literature, logistic regression, right? Logistic regression is based on the binomial distribution. The Poisson is another discrete distribution, which in certain situations actually approximates quite closely the binomial. It's very good when you have rare number of events occurring at a constant rate, and we can use the Poisson distribution. An interesting characteristic of the Poisson is that the variance is equal to the mean. Now, this is often not the case, and you often do need to have some sort of corrections, but in general, that's the way it is. And we can see actually in the graph on the right, as the rate, the lambda goes up from 1 to 4, the variance, the spread increases, right? So the mean goes up, the variance goes up with the Poisson. So with this sort of background, now let's talk a little bit more about statistical inference, which depends on these probabilities. Okay, so we've talked about some probability functions, but there are actually contrasting views about what is probability. And the most common use in medical literature follows null hypothesis significance testing, what's also referred to as the frequentist paradigm. And this views probability as a long-run frequency. If we repeat something over and over and over, how many times will it happen? And in the context of null hypothesis significance testing, it aims to answer a question is, what should I decide, given my data, and given that I want to control the long-run proportion of mistakes I make at some tolerable level? This has the appearance of being very objective, deductive in its approach, and has really held sway for the last 100 years in medical research. One can see, though, that not everything can be repeated endless times, and it seems to be a bit convoluted. So there are people that are less enthusiastic about that view of probability. There is another view of probability, which is Bayesian in nature, which views probability as some sort of calculus of your beliefs, right? And that answers questions like, given my prior beliefs and this new data, what should I now believe? Okay, according to Bayes' theorem and the laws of probability. There are numerous other comparisons between the two, which we won't go through. The main ones that I think we want to remember is how they view probability and how they look at parameters that we would like to measure, like what's the risk ratio of getting drug X as opposed to not getting drug X or whatever. And those parameters in a frequentist point of view are considered fixed, unknown, but fixed. What's variable is the data. We can vary the data by resampling countless times. The Bayesian, on the other hand, says, look, the data we have is fixed. I have this data. And what I want to measure is this parameter. And it's the parameter which is the random variable, not the data. So those are the kind of two contrasting views of the data and the parameters. Of course, the Bayesian will incorporate prior information. The frequentist doesn't. How they evaluate and make decisions, the frequentist is by p-values. The Bayesian is by posterior probability distributions. And then there's some other statistical characteristics. I have question marks at the bottom because the frequentist is not as objective as one thinks, and the Bayesian is not as subjective as is often characterized. So with that in mind, I thought, well, how well do we understand as clinicians probability? And this is a little survey that I initially sent around to cardiologists and my colleagues, and gave this talk a couple of months ago, or a variation of it. And I thought, well, since I'm doing general rounds, I would send it out to internists. What I will say is that the response rate was rather low. Now, that might be because we have to use the M.Eng emails or whatever. But I only had 4 out of, I don't know, there were like 80 people that we sent it to or whatever. So, I've just grouped the 4 GIM staff, 0 response from the residents, into with the cardiologists and the cardiologist staff and fellows. I initially came across this paper, which looked at a new approach for treating people with a failing mitral bioprosthesis. And they had 1-year outcomes with this percutaneous transeptal mitral valve-in-valve of, 0 adverse outcomes, no deaths, and no stroke. And, in 50 of them, and this was reported in one of the circulation journals. And I thought, well, geez, how unlikely is it that they could take this population and have no adverse outcomes, right? Now, this is a single arm observational study, but they claim by using the STS model, which is a very respectable model for outcomes, that had these 50 patients had a redo operation, the model would have predicted that they had a 4% mortality at 1 year, and they observed 0. So I sort of said, okay, what if mitral valve-in-valve actually has the same mortality risk, 4%? Okay. How unlikely would it be to see 0 deaths? Right? And I also wondered how my colleagues would see that. How unlikely they see that. I also was wondering, and so I designed this multiple choice questions. What's the probability of observing 0 deaths if the expected mortality in this group was really 4%, the same as the redo people? Okay, the same as the redo people would have had if they had had a redo. And I also said, well, okay, what would be the probability of seeing 0 deaths if the mitral valve-in-valve mortality was actually 40% higher than the 40%? And ultimately, a third question is, given only this study, because there really is not very much out there about mitral valve-in-valve for mitral bioprostheses, what's your probability that this new procedure is as safe or safer than a classic redo? Okay? And there's multiple choices, so I gave people choices. So in the cardiology, I had 42% response among the staff, only 18% among the fellows, and as I said, 4 GIM staff who replied. So this is the outcome. If we first look at question number 1, okay, which is what's the probability of seeing 0 deaths? Okay. The first thing, well, let's just look at the staff because there's a lot more staff. There are only 4 fellows. We can see lots of variability. Some people said it would be quite unlikely, less than 1% that we would see 0 deaths if there was a 4% rating, all the way up to being 15%, greater than 15%, even though we had 0 deaths. You can see it there, it's all over the place. Right? I mean, there's lots and lots of variability. Now, the second question says, okay, what's the probability of seeing 0 deaths if the death rate was actually higher? It was 5.6, a 40% increase. Well, almost everybody said, well, it would be less likely to see 0 deaths. And indeed, makes, I think, intuitive sense. But not everybody. Some people stayed the same. A few of the residents actually went up. A couple of staff stayed the same. One went up. Again, the people that went up, maybe they just weren't paying attention, but we can see, especially the variability, right? That people are very uncertain. How likely or unlikely is it to have 0 deaths in this scenario? Which is a bit problematic if you're actually trying to tell patients whether they should consider this new procedure or not. Now, it turns out that this is discrete data, so we can analyze this by using one of our probability distributions that we discussed earlier. And now we could do that by going a few slides back and taking those equations that I had on the left-hand side and plugging in n and plugging in, x and whatever. Or we could take pretty much any software that has distribution functions, and with one line of code in R, I can ask it to sample from my binomial distribution, 50 people with a probability of 0.4, how many times do I see 0, 1, 2, 3, 4, up to 6 events, right? Multiply by 100 just to get it into percentages. And we can see the answer is 0, the probability of, with 4% death rate, the probability for 0 deaths is 13%, right? So all those people that said like less than 1%, they're missing by an order of magnitude. You can do the same thing with one line of code with the Poisson, and you get pretty much the same answers. So the actual answer to question 1 is somewhere between 10 and 15%. Okay, bear in mind that's what we actually saw. So what about if we can plot these out, because sometimes it's easier to understand visually, but and you can also see that the Poisson and the binomial sort of tend to line up pretty closely. So what about the same question, but a 40% increase? The mitral valve and valve actually has a 40% higher mortality than standard redo. How unlikely would it be to see zero events? So we saw that most people said that that would be less likely. Again, we can do this one line of code. We're going to do it with the Poisson now, and we're going to use, instead of a 2% yearly rate, because the number of deaths, there were 50 people at 1 year, and 4% is 2. And we're bumping it up by 40%. We just put in that one line of code, 2.8. We run the same thing, and we see that even if it was 40% higher, there's still a 6% chance that we might not see any deaths whatsoever, right? So when we can see that, as expected, if the death rate goes up, the curves shift to the right, and the probability of observing 0 deaths will fall. So the answer to question 2 is 5 to 9%. Lest we forget, if we look at question 2, we still are pretty much all over the map. The idea here, and what I'm trying to get at, is that, you know, if we're going to have this data in front of us, we should have some feeling for what it means. Does this provide good evidence that there are going to be 0 deaths with this new technique, or is it, how much uncertainty do we have? And that's a little bit what the final question was rather than looking at specific points, is how cumulatively, what's the probability that the valve-in-valve mortality was less than 4%, less than the predicted mortality for redo? And are we 25% sure that it's less? Are we 25 to 50%? Are we more than 50% sure that it's safer? Now, again, I'm not proposing that we should be doing valve-in-valve. There are many other things. There are side effects, there are costs, or whatever. We're just looking at one part of the equation, just the pure efficacy of whether you stay alive. And again, we see this variability. Right? And so ideally, what we would like would be to have an RCT, right? Where people are randomized to get valve-in-valve or to get a redo. But we don't have the RCT, so we're doing the next best thing. I'm going to assume that the model, the STS model, for what the mortality would have been if there was a group that had a redo was 4%. So I have my 50 patients who got their mitral valve and valve, and generated 50 patients who had a redo, gave them a 4% chance of mortality, and then just did the same thing we did before, just the binomial, dead or alive, right? Only now we're putting in the same way as when we have linear regression and we want to measure height, and one of the predictors was we'll put the father's height on the right-hand side. Here, we want to predict whether they're dead or alive, and our predictor, in this case, is going to be treatment, right? And it's just a standard sort of thing you would do with linear regression, except that we're doing it with a binomial distribution, so it's logistic. We run this line of code, and hard to see, but here is the treatment coefficient, minus 4%, which is that the mitral valve and valve has a 4% lower mortality, which makes sense because we put in, essentially, we were assigning not everybody getting exactly 0 for the mitral valve and valve, but that's where they were headed, and the redo people was 4%. But this also allows us to calculate the uncertainty around that estimate, right? The credible interval. And we see it goes from minus 13% to plus 3%. We can actually plot that in terms of a probability distribution, right? Which is what we've done here, okay? Centered on minus 4%, with the spread going from minus 13 up to plus 3. And now we can measure, integrate the area underneath the curve. And we can look for how much of the area is to the left of 0. In other words, what's the probability that mitral valve and valve has less mortality, right? This is all from one line of code, right? And it turns out to be 88%, right? So we're 88% sure that there is less mortality. I haven't quantified how much, but less based on this data, provided the model prediction of 4% for the redo people who didn't get a redo is accurate. But it gives you some feel. I'm not saying, again, I'm not trying to put forward that this is the definitive answer, far from it. But it's just to give you an idea of how we should be thinking about this data, and how sure are we, and what's going on here. So how did we do? Question 1, how likely was it to see 0 deaths? About a quarter of the people got in the right range, 10 to 15%. But about a third of them thought it was less than 5%. Question number 2, most people, at least 2/3, realize that if the mortality is going up, we're less likely to observe 0 deaths. But about a quarter didn't. But only approximately 10% correctly estimated that the probability, based on this data and this data alone, that mitral valve and valve was as safer than a redo. Only about 10% put it in the right range. And 2/3 of people put this probability that was estimated at 88% to be under 50%. And nobody gave all 3 answers correct. So, small sample size, self-selected. Were these people better or worse than, the general population of cardiologists and GIM staff? I don't know. I mean, this is nothing that you would try and submit to the New England or anything. But I think it does suggest, notwithstanding these limitations, that some additional quantitative probability training could possibly be helpful. So what about this infamous p-value? I suspect that most people in the audience have had at least one and probably several talks about p-values and their limitations and whatever. Just to go back over some of it again, just recall that it's the probability of seeing your data or more extreme data, given that the null hypothesis is true. But it's also dependent on what is the probability distribution that you are assuming. And very few times do people also consider that in the limitations of where your p-value is coming from. So And the figure here is the same figure we've seen before, where Z value minus 1.96 up to plus 1.96 is at 95%. And so each of the tails has 2.5%. And what we call the Z value is like the effect size divided by the standard deviation. And so this is on a normal 0-1 distribution, but any distribution can be transformed to a 0-1 with just a simple transformation shown at the bottom of the caption. Okay, so this is what the p-value is like. We see here is how to calculate it. Okay, we say, let's look at the p-norm. P-norm is just the cumulative distribution up to point Z, okay? So it says, what's the value up to point Z, that area, and so 1 minus it is that area at the extreme right, is 2.5%. Because we also want to take it down here, we multiply everything by 2. That's how we calculate this, right? Okay. So here was a question number 2. We have an experiment which is actually gives quite an encouraging result. It gives an effect size that are 2 standard deviations, or 2 standard errors rather, removed from 0. Right? So there's an effect. And I'm giving you this is the true effect. We know this. Somebody, Oracle, has told us it is 2. Right? There are some measurement errors. Okay. There's a standard error involved in the measurement, but we're 2 standard errors away from 0. So imagine this experiment is repeated 10 times with this true value of 2. Now, there's going to be a sampling errors involved. When you calculate the p-values associated with this effect and that standard error, what do you think is the range of these 10 p-values, right? 0.02 to 0.05, all the way up to 0.0002 to 0.5, right? What do you think the range of that is? Well, again, we can do it with 1 line of code. We said, this is the exact same formula that was on the preceding page, 2 times 1 minus the cumulative function of Z. Okay, well, what's Z here? Well, Z is 10 times we are randomly drawing a point Z from a distribution, the mean of 2 and standard error of 1. We're doing that 10 times, and we're going to calculate our p-value 10 times, and then we're going to print the p-value out. And it goes from 0.0002 up to almost up to 0.5. It's a huge discrepancy. Okay, a p-value is a very noisy parameter. Okay, it is very noisy. How did we do? Well, we had fewer responses on this one. We only had 17 responses, and about a quarter of people got it right, and 3/4 didn't. The majority thought the p-value would be, pretty close to around 0.05 in that vicinity. So how can this be? How do we? Why are we making this error or whatever? And so this is the data that we actually have. We're told that there was an effect of 2, so that's the maximum. There was a 1 standard deviation error, so 2 standard deviations away. So we can see we're 2 standard deviations away. That's our data. Those 10 points were randomly drawn from that distribution. Now we come along and say we're going to analyze this in p-values. So what's the p-value? Well, it's given the null hypothesis is true. So now these red dots are going to become blue dots. Okay? They're not changing position, but they're becoming blue dots. And we're looking at them through the lens of this P distribution centered on 0. And you can see that if we go up to a p-value of 0.05, which is the Z value of 1.96, that there's a whole bunch of them that are on the wrong side. It turns out that about half the time, we're going to get this p-value being greater than 0.05, telling us we should accept the null of no effect when we know, when we drew the data from a distribution that was 2 standard errors away from the null, right? This is, what the p-value is doing. It's making us look at some distribution that is of no interest whatsoever to our data, right? So it's not surprising. Whoops. I'm not. Oh, okay. So, okay. So, I mean, this is tricky stuff. So what might you do? You might sort of say, okay, Brophy's bothering me by sending me all these emails that I haven't responded and whatever. I'm going to just put this into chat GPT-4 and get the answer and be done with it. And so if you ask chat GPT-4, they say, well, if you assume minor variations around the 2 standard error effect, p-values might typically range from just below 0.04 to slightly above it. And so we would expect somewhere between 0.04 and 0.05, right? Which is not at all what we've just shown with that simulation. So I then showed chat GPT-4 the simulations. They said, your simulation highlighted a variability that can occur. Yes, which indeed can lead to a much broader range of p-values. It demonstrates that even if the true effect size is relatively large, the exact p-values obtained can vary widely. Okay, so yes, that is correct. So I said, if I ask you the same question tomorrow or in the future, will you update your response accordingly? And they said, yes, my response will certainly take into account this discussion and the insights from your simulation. Yeah, very polite. 1 week later, I asked them the same question, and it gave exactly the same answer between 0.04 and 0.05. Okay, exactly the same answer. So all that to say, it's not surprising we have trouble with just our gut feeling about what the p-value should be in this experiment. Okay, I mean, it's tricky stuff. And we need more than just our gut to help guide us in the interpretation of these things. So from that, the larger points here are that the p-value is a statement relative to the null hypothesis of no effect. Doesn't have much of a meaning or interpretation relative to a real non-zero effect that we're looking for. It's some weird transformation of the Z-score with, I guess we could definitely say with very non-intuitive behavior, and it's super noisy. And even, large language models don't realize how noisy these p-values are. And I would say, just because I like the pretty little graph that I did, you can learn a lot from doing simulations. And simulations are actually quite easy to do. So with that in mind, just close with one example. Those of you that know me know that I probably couldn't get through the talk without some sort of Bayesian mention. But we've seen the problems that arise, with p-values. And I would say that Bayesian approach does avoid some of these problems. There are some other disadvantages, this whole question about subjectivity, how do you deal with priors, but you can be transparent with that. There's a classic problem of induction and that, but nevertheless, I think there are some advantages to be had by going in a Bayesian route. So I thought that I would ask my colleagues, since we've been looking at probabilities, but really probabilities of single arms, let's look at a study where we actually do have data on two arms, right? An RCT published in the New England that concluded, as you see here, this was looking at out-of-hospital cardiac arrest and whether extracorporeal CPR was better than conventional. And they concluded that they had similar effects on survival. And that's the data. The p-value, which they gave rather prominently, is 0.52. So this is led to the conclusion that whether you get extra corporal CPR or conventional CPR, that it's similar effects. So I thought I would ask again my colleagues what they thought of that. And so I said, based only on this study, which we're assuming is of high quality without bias, what's your probability estimate that the extracorporeal CPR is better than CPR? And only, well, two people, two of the 18, I think we were 18, said it was probably greater than 50%, but the bulk of people, I think, being influenced by that p-value of 0.5, thought that there was a less than a 5% chance that the CPR was better than CPR. I then said, look, there have been two previous trials that have looked at this question, and both trials showed improved 30-day survival with the extracorporeal CPR. So can you now update your probability that the eCPR is better? And indeed, there was a shift to the right. But in terms of those that had thought that it was greater than 50%, we went from 2 to 5. But collectively, it's sort of 2/3, 13 out of 18 were still less than 50% that the extracorporeal has a more than 50% probability. So what happens if we actually do this from a Bayesian point of view? Again, this is just logistic regression, the binomial model. And all the colored lines are showing what the individuals did. They chose, and then with the new data, their probabilities increased. If you actually analyze this, probabilistically, you start off that you're more than. So what we can see here is that while the original authors claimed there was similarity between the two techniques, based just on their data alone, there was actually a greater than a 50% probability that the extracorporeal had better survival. That's not 95%. It's not a p-value of 0.05, but there was a greater than 50% probability that the new was better. Now, why didn't they see it? Well, it's quite obvious. It's because the study was underpowered, right? So you don't have enough power to actually get where you want to go. That the extracorporeal is superior. Now, the New England paper, of course, references these other studies, but never tries to actually formally incorporate it. The MUHC cardiologists did incorporate the data and appropriately increased their probability that the extracorporeal was going to be better. But their low original estimate had this sort of grounding effect, so that they, at the end of the day, they sort of said, okay, well, maybe with this new data, there is at least a 50% probability that the extracorporeal in this particular population, again, I'm not saying that we should be using this across the board, but just for the particular populations that were studied, but they come up to about 50%. As opposed to what the calculations are, which are 95%. The conclusions are that your gut heuristic probability estimates vary widely, and they're often very far from what is the probabilistic quantified effects, right? And the statistical literacy depends on this appreciation and understanding of some underlying probability distributions. But I think that statistical literacy can improve our diagnostic and therapeutic decision-making. And finally, I think that our medical education should consider improving or adding to our quantitative training as we move into the deep learning and everything else, that we have a better feel for what these statistical models say, what probability is, what uncertainty is, and what are sort of reasonable ranges. Just acknowledgements to my PhD supervisor, who Nancy knows very well, Lawrence Joseph, who arguably is Canada's first Bayesian biostatistician. I had the good fortune of running into 30 years ago. And also FRQS, who supported me for many years and allowed me to pursue these statistical musings. There are a bunch of references. There is actual code in R in all these papers online. You can go and get it, and I'll give you the code. And if you actually want the code for the slides, I can give you that. And now finally, my dog. Yeah.
Thank you so much, Dr. Brophy. Jay, really a great pleasure as always to listen to your lectures. And you see now the picture of your dog. Thank you for sharing that with us. There's a nice comment there from Sasha Bernatsky saying, Dr. Joseph told me once, James Brophy is the smartest man I know. And I think I've heard that from other people. So thank you very much for sharing all this with us. Practical people can enter the questions in the chat while we look at your beautiful dog there. Jay, so how do we, what do we do practically speaking when we conduct studies? Certainly, let's start internally, at least conduct studies from within. Is there sort of a team that we can speak to help us with these, to make sure that we're on the right track in terms of the statistics that we should be looking at and our power calculations?
Right. So yes, I think there are lots of people who have the skill set, within core to help guide you and get you on the right track. I think we're very, very fortunate in the association with the EBOH and people within core that have the skill set to help you out. But I think we really want to actually even go more upstream than that. And, when we write our grants and we want to get a grant, we're kind of more or less obliged to do a bit of a meta-analysis of what already exists, right? To sort of show that there's a reason, a place for us to do this study. Yet, when we do our RCT, our incentive system is such that we want to present these results standalone by themselves, and this is it. Here we are. This is my RCT, and damn it, it is on its own merits. We should, I think, have the same sort of mindset that says, look, if there have been other RCTs which are in the same ballpark as yours, then you should be analyzing your data in conjunction using the priors from these other studies. Now, you might say this prior study was not very good, so I'm only going to give it 5% of its total actual weight. Or you might say it was actually identical, so I'm going to use all the data in there. But, until we start thinking cumulatively, we're doomed to these sort of one-offs, looking at small studies that aren't quite powered and making all sorts of incorrect inferences. I think we really should. And the other advantage of that, I will point out, is that you can, if you are ready to say, look, the prior data is not conclusive, but there is some sort of signal there. If I add my data in there, I can, depending on the assumptions, get a definitive answer, yes or no, so that you can perhaps do your RCT with fewer patients, which means it costs less, which maybe means we could do more RCTs if we were willing to accept prior information and analyze things in a Bayesian light rather than being stuck in the frequentist mode, which does not consider any point in time the prior information, other than with a few words in the discussion, and the reader is left to try and, according to his gut, bring all this information together. I really think that that's a step that we should be taking to try and change the incentives around how we fund research and what we expect people to do with the results. We've got to the point where we said we want to see a systematic review and a meta-analysis before we fund you, but then we're going to let you do your results and just report it on its own. To me, that's not logical.
Fair enough. I understand.
That's one thing I think from a big global effort we should do. And on a more micro level, I think we do have to talk more and acknowledge uncertainty, right? But, individual researchers don't want to acknowledge it. Research institutes don't want to acknowledge it. They want to be able to say, we showed this, right? So give us money, please, all our funders, and whatever. They don't want to say, we contributed a little bit here. We've narrowed our uncertainty down from, being a coin toss to being, 75, 80% in favor of this new. No, they don't want that. So I think there are many places where we have to reassess our thinking and what our incentives are.
There's a question here in the chat. How do you take publication bias into account in determining priors?
So I think the thing about priors is to, one, make them totally transparent, right? First of all, so that people can see exactly what you've done. And that way they may or may not agree with you, but at least they know where you're coming from. The other thing I think you want to do is you want to take what is called in the stats literature a community of priors, right? From a very skeptical prior, okay, which would, by its very nature, almost be incorporating the unpublished studies, which generally are negative studies. So you take a very skeptical prior. You can take a prior from a meta-analysis, a well-informed prior. You could take an enthusiastic prior. And so you can look at what you get the posterior from all three of those priors. And if they're still widely divergent, it tells you, what, we haven't reached a consensus and we do need more data. But if independently of where the prior was that you started with, once you've added all this new data that you've collected, they all sort of converge into one posterior, then you feel quite comfortable that, yeah, you know what, we have enough data to actually make some statements, right? So I think, the unpublished would be by, making sure that you have a skeptical prior included in your community of priors. I think whenever you do a Bayesian analysis, you really have to show at least three or four different priors and see how the posterior changes. But it's really key to be transparent, because so many of what the frequentists are said as objective. But as I said, there's all sorts of assumptions that have gone into the model they've chosen. It's just that none of their assumptions are ever declared. The Bayesian is declaring up front what his assumptions are, and then he's being characterized as being subjective. The frequentist just sweeps it all under the table and is then known as being objective.
Makes sense. Jay, we're coming up on the hour, so we will have to close the rounds. I thank you very much. As always, there's a lot to learn from listening to your lectures. Congratulations on everything that you've done to advance this field. And I thank everyone for joining us today, and have a great afternoon, everyone. Thank you, Jay. Sorry for the
Absolutely.
technical difficulties. Thank you. Bye-bye. Bye.